Welcome to lecture number 9. In our final 3 lectures, we're going to be talking about a type of mathematics which is called calculus. We'll start by talking about limits and continuity, and then we'll introduce the idea of differentiation and then some rules that we can use when we're doing our differentiation. First, the idea of limits. Think about this function, x squared minus 1 divided by x minus 1. The domain of this function is all of the real numbers except 1, because we can't divide by 0. This is a graph of the function. Because the function is not defined when x is 1, we have a hole in the graph when x is 1. And then the question I want to ask is, how does this function behave when x is close to 1? We know that x cannot be equal to 1 because the function is not defined when x is 1. But how does it behave when we are close to 1? Let's make a table of values. First of all, let's look at x is 0.9 and x is 1.1. Well, we can put these into the formula. X squared minus 1 divided by x minus 1. And we find that if x is 0.9, then f of x is 1.9. If x is 1.1, then f of x is 2.1. Let's go a bit closer. Let's go closer to 1. How about 0.99 and 1.01? Now we're pretty close to 1. Again, we can put these numbers into the formula for the function and we can calculate f of x. If x is 0.99, then we can calculate f of x is 1.99. If x is 1.01, we can calculate f of x is 2.01. I think I'm understanding what's happening. It looks like if x is close to 1, then f of x is close to 2. Let's go even closer and see if that's still true. 0.999, that gives f of x is 1.999. If x is 1.001, then f of x is 2.001. So yes, it looks like if x is close to 1, then f of x is close to 2. We have a particular way of writing this in mathematics. We write this as a limit. We write LIM for limit, and then underneath we write x arrow 1. And then our function f of x is equal to 2. And the way we read it is the limit as x tends to 1 of f of x is equal to 2. This means that if x is close to 1, very, very close to 1, but crucially not equal to 1, then f of x is close to 2. Back to this function. Now note that, as I've just said, the limit as x tends to 1 of f of x is equal to 2, but this function is not defined that x is equal to 1. Let's look at a different function. Now I'm defining g of x to be x squared minus 1 over x minus 1, same as before, if x is not 1, but I'm adding in the point 1 if x is equal to 1. The limit is still 2. The limit means how does the function behave if x is close to 1 but not equal to 1. So if we're doing the limit, we can ignore the value when x is 1. We're only interested in x is close to 1 but not equal to 1. And just as the function f, we have that the limit of g is equal to 2. If x is close to 1 but not equal to 1, g is close to 2. But note here, g of 1 exists and g of 1 is not equal to 2. One more function, a function h. h of x is equal to x plus 1. How does h behave if x is close to 1 but not equal to 1? h is close to 2. So the limit as x tends to 1 of h of x is equal to 2. For this function, that's the same as the value of h at 1. H of 1 is equal to 2. Let's go to another function. The function f of x is equal to x. Pick any number, x0. How does the function behave if x is close to x0? Well, because f of x is just equal to x, the function must be close to x0. We can write that the limit as x tends to x0 of x is equal to x0. If x is close to x0, then x is close to x0. Of course it is. How about a constant function? Any number, I've chosen the number 13, but it could be any number. And any value x0 on the x-axis. If x is close to x0 but not equal to x0, how does the function behave? Well, the function is always equal to 13. If x is close to x0, 13 is close to 13. So the limit as x tends to x0 of a number is equal to the same number. Now, limits don't always exist. Think about these two functions. U of x is 0 if x is negative and is equal to 1 if x is positive. Or v of x is 0 if x is negative and equal to sine 1 over x if x is positive. First, the function u. Here's a graph of the function u. The limit as x tends to 0 of u does not exist. Let's understand why that's true. We need to look at x, which is close to 0 but not equal to 0. First, let's look on the left. So first, let's look if x is close to 0 but x is strictly less than 0. Then u is equal to 0. Next, let's look on the right. If x is close to 0 but x is positive, then u is equal to 1. But 0 is not close to 1. It's not possible to find some number that the graph is always close to if x is close to 0. So the limit as x tends to 0 cannot exist. The second function, the function v, the limit as x tends to 0 of v of x does not exist because this function oscillates up and down, up and down, up and down, up and down too quickly if x is positive and x tends to 0. There does not exist one number that the function always stays close to. It doesn't matter which number we pick. Let's say we picked this number. It might be close to it, but then it goes away, and then close to it, and then away, close to it, and away. It's not always close to this number L if x is close to 0. So the limit does not exist. We have some rules for limits called the limit laws. First of all, I need 4 numbers, let L, M, C, and K be numbers. I need 2 functions, we'll call them f and g. And I want to suppose that the limit as x tends to c of f of x is equal to L, and the limit as x tends to c of g of x is equal to m. The first rule is called the sum rule. The limit of f plus g is equal to L plus m. That's good. If we have got 2 functions to add it together, we could take the limits separately and then add them together. The difference rule is almost the same. The limit of f minus g is equal to L minus m. Constant multiple rule. What do we get if we take a function f and we multiply it by a number k and then take the limit? We just get k out. The product rule, the limit of f multiplied by g is L multiplied by m. The quotient rule, I have to be a little bit careful here. This is only true as long as m is not equal to 0. The limit of f divided by g is L divided by m. The power rule, the limit of f to the power n is L to the power n. And a root rule, I'm being a little bit careful here. This only works as long as the nth root of L exists, because of course we can't do the square root of a negative number. So as long as we're not that, as long as the nth root exists, the limit of the nth root of f is equal to the nth root of L. These are hopefully all straightforward. So for example, if I wanted to find the limit as x tends to 2 of x cubed plus 4x squared minus 3, the first thing I can do is I can use the sum and difference rules to split this up into 3 small and easy limits. And then I want to use the power and the constant multiple rules to make these easier. I have the limit of x all cubed plus 4 times the limit of x all squared minus the limit of 3. We know these limits. The limit of the identity function as x tends to 2, of course, is just 2. The limit of a constant function, here we have the limit of 3, is just that number. So just 3 here. Let's do one more. Find the limit as x tends to 5 of x to the power 4 plus x squared minus 1 divided by x squared plus 5. I have a function divided by a function. So first I want to use the quotient rule to split this up into 2 limits. The limit of x to the power 4 plus x squared minus 1 divided by the limit of x squared plus 5. And then I'm going to split it up further by using the sum and difference rules. And at that point, it's easy. Just use the power rule. We have 5 to the power 4 plus 5 squared minus 1 divided by 5 squared plus 5. That's great, but is there an easier way than doing it like this and saying which rule we're using at each step? If we have a polynomial, the answer is yes. If P is a polynomial, then the limit as x tends to c of P of x is always equal to P of c. And we have the same thing for a rational function. If P and Q are polynomials, and be careful here, as long as Q of C is not 0, because we can't divide by 0, then the limit as x tends to c of P of x over Q of x is equal to P of c over Q of c. So that makes some limits easier. For example, this one. Calculate the limit as x tends to minus 1 of x cubed plus 4x squared minus 3 divided by x squared plus 5. We have a rational function. It's a polynomial divided by a polynomial. And on the bottom, we're not going to get 0. So we just use the theorem. Every time you see an x, just replace the x by minus 1. Minus 1 cubed plus 4 times minus 1 squared minus 3 divided by minus 1 squared plus 5. And when we calculate this, we get the answer 0. Anytime we have a rational function and the limit of the polynomial on the bottom is not 0, we can just substitute in c for x and get our answer. But what do we do if we do get a 0 on the bottom? What can we do if Q of c is equal to 0? Let's look at this example. The limit as x tends to 1 of x squared plus x minus 2 divided by x squared minus x. If I just replaced every x by 1, then I would get 0 divided by 0. And this is not what we want. We never, never, never want to get 0 divided by 0, because 0 divided by 0 is not a number. So what can we do here? Instead, we can try to factor our two polynomials. Right, we're going to assume in the following calculation that x is not equal to 1. We can always do that because, let me remind you, if we have limit as x tends to 1, that means how does the function behave if x is close to 1 but not equal to 1? Always not equal to the value of c. So we know that we would always have x not equal to 1. Okay, now looking at the line I'm putting in the blue box, we can factor the top to x minus 1, x plus 2, and we can factor the bottom to x, x minus 1. But then there's an x minus 1 on the top and an x minus 1 on the bottom. Cancel these out, and we're left with x plus 2 divided by x. And that's a lot easier to take the limit of. Now when we don't have a 0 on the bottom, so we can just replace every x by the number 1, and we can get our answer. The next idea for limits is a theorem called the Sandwich Theorem. And the picture for the Sandwich Theorem looks like this. Let's suppose we got three functions. A red function, a blue function, and a green function. And I want to suppose that the blue function is in the middle. It's sandwiched between the red and the green functions. And to be more precise, we only need that to be true close to C. If we're way off on the left, it doesn't matter what the function does. It doesn't matter if the functions just cross over, one is above the other, it doesn't matter. All that I'm really interested in is this true close to C? Do we have the green function on the bottom, the blue function in the middle, and the red function on the top, close to C? Right, the theorem looks like this. Suppose, first of all, that f is smaller than g, smaller than h, for all x close to c, but because this is limits, remember we always have x is not equal to c. And suppose that f and h have the same limit as x tends to c. We go back to the previous picture. Now I'm going to clean it up. When x is close to c, f and h are both close together. They have the same limit. If that's true, then the theorem says that the function in the middle, which is sandwiched between the f function and the h function, must have the same limit as well. Go back to the picture. If the red function and the green function get really close, how close? As close as we want when we're close to C. And if the blue function is sandwiched or squashed between them, then the blue function must have the same limit. We can use that to answer questions like this. Let's suppose we're told that this inequality is true for all x close to 0, but not x equal to 0. And then we're asked to calculate the limit as x tends to 0 of the function in the middle. The function in the middle is quite complicated, but that doesn't matter because on the left and on the right we have some easy functions. The function on the left, if we take the limit as x tends to 0, we get 1. Function on the right is just number 1, and the limit of 1, of course, is just 1. that means that the function in the middle is sandwiched between or squashed between two functions which have the same limit, two functions which both have the limit 1. So straight away we could use the sandwich theorem to say the function in the middle must have the same limit. The function in the middle must also have the limit 1. Before I go on, if you use a named theorem in the exam, then you need to say which one you're using. So if you were given an exam question like this, make sure you write by the sandwich theorem somewhere in your answer if you want to use the sandwich theorem. A similar theorem before we finish this chapter. Let's suppose we just have two functions, f and g, and let's suppose that f is always less than or equal to g for all x close to c. So let's suppose f is this red function. Let's suppose g is a green function. And let's suppose c is about here. We don't care what happens a long way away from c. We're only interested in what happens if we're close to c. So let's suppose we're between these two dotted lines. Between these two dotted lines, the green function is bigger than the red function. We're going to suppose that the limits of these two functions exist. Then the theorem tells us that the limit of the smaller function must be less than the limit of the bigger function. Let's move on to the next chapter. The next chapter is about continuity. What does that mean? The idea is, when can we draw the graph of a function without lifting our pen off the paper? So just imagine for a moment that I'm drawing this graph. Let's imagine this is my pen. I can put my pen down on the paper. I can draw this graph all in one go. I don't need to lift my pen up. But if I was drawing this function, again, I could start over on the left with my pen. I could draw along the graph. No problem so far until I get to C. When I get to C, I have to lift my pen up, move my pen, and then put my pen back down on the paper to draw the next part of the function. If we have to lift our pen off the paper, then the function is not continuous. That's the idea, but this is mathematics. We need to be more precise than this. A function f is continuous at a point C if the following three conditions are all satisfied. We need to have that f of c exists. We need to have that the limit as x tends to c of f of x exists. And these two numbers must be the same. If f is not continuous at c, then we say that f is discontinuous at c, or equivalently, we can say that c is a point of discontinuity of f. Have a look at this function. F has the domain closed interval between 0 and 4, and the graph is shown above. Where is this function continuous? Where is it discontinuous? First of all, let's look at c equal to 0. Is the function continuous at 0? The answer is yes. Why? Because f of 0 exists and it's equal to 1. The limit of as x tends to 0 of f of x exists and is equal to 1. And these two numbers are the same. So the function must be continuous at 0. Next, let's look at between 0 and 1. Is the function continuous if c is between 0 and 1? Yes. Two ways to think about it. Either I could draw this piece in one go without lifting my pen, or in terms of the definition, f of c exists, the limit as x tends to c of f of x exists, and these two numbers are the same. What about at 1? Is the function continuous at 1? No. If we think about drawing with our pen, if we were drawing this graph, when we got to 1, we'd have to lift our pen off the paper, move our pen, and then put it down again. Or in terms of mathematics, it's not continuous here because the limit as x tends to 1 of f of x does not exist. Let's continue. If we're between 1 and 2, it's continuous. The limit exists, the function is defined, and then equal. Is it continuous at 2? No. Why? F of 2 exists, and it's equal to 2. The limit as x tends to 2 of f of x exists, and it's equal to 1. But we fail rule number 3. These two numbers are not the same. Is the function continuous between 2 and 4? Yes. Is it continuous at 4? No. Same reason for at 2. The limit is different from the value of the function. F with domain closed interval between -2 and 2, f of x is the square root of 4 minus x squared. This function is continuous at every c between -2 and 2. This function g has a point of discontinuity at c equal to 0. It's continuous at every other point. This function h is continuous between -infinity and 1. It's continuous between 1 and 2, and it's continuous between 2 and infinity. It's not continuous at 1, and it's not continuous at 2. What is the difference between the empty circles and the closed circles? It's the value of the function at that point. What is g of 0? Well, 0 is in here. 0 is greater than or equal to 0, so the function is equal to 1 here. To show that the function is equal to 1, we use a filled-in circle where the function is where the value of the function is, and we use a open circle or a hole where the function is not equal to. If a function is continuous at every point in its domain, then we just call it a continuous function. Time for a theorem. Let's suppose f and g are both continuous at c. Then f plus g is also continuous at c. F minus g is continuous at c. K multiplied by f for some number k is continuous there. F multiplied by g is continuous there. F divided by g is continuous at c, as long as we're careful that g of c is not 0. F to the power n is continuous at c. For the nth root of f, we need to be a little bit careful. You don't need to worry too much about this. This is just me being careful. I need the nth root of f to be defined close to c. If that's true, then the nth root of f is also continuous at c. For example, every polynomial is continuous. continuous for every number, so it's continuous. It's a continuous function. If P and Q are polynomials, and if Q of C is not equal to 0, then the rational function P divided by Q is also continuous at C. Sine and cos are continuous. Composites of two functions. If I write G composed with F, or G circle F, this means first we do the function F, and then we do the function G of the result. So G of F of X. Theorem: if F is continuous at C, and if G is continuous at F of C, then G composed with F is continuous at C. So we can think of the picture like this. If we think of functions as arrows, the blue arrow is continuous, the green arrow is continuous. That means that the red arrow must be continuous. For example, show that the square root of x squared minus 2x minus 5 is continuous on its domain. We have two functions here, two continuous functions. Square root of t is continuous. X squared minus 2x minus 5 is a polynomial. All polynomials are continuous. So we have a continuous function of a continuous function. That must be continuous. Show that x to the power 2 over 3 divided by 1 plus x to the power 4 is continuous. Well, we have a continuous function and another continuous function. It's a continuous function divided by a continuous function. And the function on the bottom is always not equal to 0. So the function must be continuous. Next theorem. If G is continuous at B, and if the limit as x tends to c of f of x is equal to b, then the limit as x tends to c of g of f of x is the same as g of the limit of f of x. What that means is, as long as g is continuous, we can swap g and the limit around. As long as g is a continuous function, we're allowed to do this. So for example, we could use that to calculate this limit. The limit as x tends to pi over 2 of cos of 2x plus sine of 3 pi over 2 plus x. Cos is a continuous function, so we can swap the positions of cos and limit. After we've used the sum rule, we have cos of two limits. The first one is easy. First one is just pi. For the second one, I have limit of sine. But sine is also a continuous function. If we have a continuous function, we're allowed to swap the positions of the limit and sine. Instead of writing limit of sine, we could write sine of limit. That's enough about continuity and limits for now. Let's start talking about differentiation. I imagine you've seen this sign out while you're driving your car. What this means is if you travel forward 100 meters, the road will go up 3 meters. In mathematics, we write this as slope is equal to 3 divided by 100. More generally, if we had a green line like this, and if we could draw a triangle underneath the green line and measure A and B, the slope of this green line is B divided by A. I have more examples. The slope of this green line is equal to 1, because that's 3 divided by 3. The slope of this line is 2, 4 divided by 2. Or is the height of the triangle divided by the base of the triangle, if we're going upwards. If we're going downwards, we use a negative number for the height of the triangle. The slope of this green line is minus a half. Okay, that's great, but most of our functions are not straight lines. How could we calculate the slope of this blue function at x0? What I could do is I could draw a green line which just touches the blue function at x is x0. We know how to calculate the slope of the tangent line. It's just height divided by its base. And what we say is that the slope of the function, slope of the blue function at x is equal to x0, is the same as the slope of the tangent line at x is equal to x0. So for example, if we looked at the function x squared, and if I had, say, x is equal to 1, I could draw the tangent line. The slope of this tangent line is equal to 2. So the slope of the blue curve at x equal to 1 is also equal to 2. Here's the tangent line to the blue function when x is 0. The slope of this orange tangent line is 0, so the slope of the blue function is also equal to 0 when x is equal to 0. And one more. Let's suppose we ask what happens when x0 is equal to 2. The slope of this red line is equal to 4. So the slope of the blue function when x0 is 2 is also equal to 4. Okay, great. If we know the slope of the tangent line, then we know the slope of the function. But how can we calculate the slope of the tangent line? Let's go back to just any function with a tangent line. How could we calculate the slope of the green line if we only know the value of the function? What we could do instead is we could look at this orange line, which joins 2 points together on the function, on the graph of the function. Let's suppose it joins the values at x0 and x0 plus h for some number. So then here we have f of x0, and then here we have f of x0 plus h. We can then measure or calculate these two distances. At the bottom, the distance between x0 and x0 plus h is just h. On the left side, the difference between f of x0 plus h and f of x0 is f of x0 plus h minus f of x0. So now we know the height of the orange line and we know the width of the orange line. Using those, it's easy to write down the slope of the orange line. That's height of the triangle divided by base of the triangle. F of x0 plus h minus f of x0, all divided by h. Okay, great. It's easy to calculate the slope of the orange line, but we don't want that. We want the slope of the green line. Look what happens if we make h smaller. As h gets smaller and smaller, the slope of the orange line gets closer and closer to the slope of the green line. In fact, if h is very, very small, then these are going to be approximately equal. The slope of the green line will be approximately equal to the slope of the orange line. And we know the slope of the orange line. We have a formula for the slope of the orange line. As h gets smaller and smaller, the slopes of these two lines will get closer and closer together. We started today's lesson by talking about this, about functions getting closer and closer to a number. So this is the idea of a limit. We can use this to calculate the slope of the tangent line, that means the slope of the function, at the point x0. This is called the derivative of the function f at the point x0. What we do is we take the slope of the orange line, and then we take the limit as h tends to 0. And that gives us the slope of the blue function when x is equal to x0. The way that we write this slope, or this derivative of f, is we write this as f prime. So for example, let's suppose we're looking at the function g of x is equal to 1 over x, as long as x is not equal to 0. I want to calculate the derivative of g, or I want to calculate the slope of the graph of g when x0 is not equal to 0. So I start with the definition. G prime is equal to the limit as h tends to 0 of g of x0 plus h minus g of x0, all divided by h. Put the function in. G of x0 is just 1 divided by x0. G of x0 plus h is 1 divided by x0 plus h. And this is going to be all over h. Now what we can do is we can rearrange this so that everything is over the same. Just as if we were trying to do a half plus a third, we would put everything over 6. We would write this as 3 over 6 plus 2 over 6. So just do the same thing here. Write the functions on the top as x0 over x0, x0 plus h, and then minus x0 plus h divided by x0, x0 plus h. Of course, the x0s cancel. We'd have minus h on the top, but then there's an h on the top and an h on the bottom. These are going to cancel out, and we're just left with minus 1 on the top and x0, x0 plus h on the bottom. At this point, we can just replace h by 0 to get minus 1 over x0 squared. The derivative of 1 over x is minus 1 over x squared. Let's look at the graph to see if this looks right. First, let's look at the green line. If x is equal to 2, we can calculate g prime of 2 Using our formula, that's minus 1 divided by 2 squared, or minus a quarter. Does that look about right? Does it look like the slope of this green line is minus a quarter? Yes. What about the red line? If we put the number 1 into our formula, we get g prime of 1 is equal to minus 1. And that looks right. It looks like we have a line of slope minus 1. So the blue function has slopes minus a quarter and minus 1 at these 2 points. If f prime of x0 exists, then we say that f is differentiable at x0. If we have a function which is differentiable at every point in its domain, then we just write that f is differentiable. Now, if we have a differentiable function f, then that means that we have a new function f prime, which has the same domain D. F prime is called the derivative of f. So let's look at this example next. Differentiate the function f of x is equal to x over x minus 1. In other words, find the derivative of x over x minus 1. So we start with our definition. We start with f prime of x is the limit as h tends to 0 of f of x plus h minus f of x divided by h. F of x is just x over x minus 1. For f of x plus h, I've written at the top, this is the same, but replace every x by x plus h. So x plus h over x plus h minus 1. I'm going to skip the details here, rearrange this and simplify it as you can to get to this point, and then replace h by 0, and we get our answer, minus 1 over x minus 1 squared. There's many ways to write the derivative of y is equal to f of x. These are all the same. F prime of x, or y prime, or dy dx, df dx, d dx of f of x, y dot, or f dot of x. Now, calculus was started by 2 men, Newton and Leibniz, and they both said that they were the first person to think of calculus, and because of this, they ended up hating each other. So Isaac Newton uses this dot notation, f dot and y dot. Gottfried Leibniz used the df dx and dy dx notation. Many years later, perhaps 100 years later, f prime and y prime notation was introduced by Lagrange. If we want the derivative of a function at a particular point, we can write it in any of these ways. We can write f prime of at x0, or dy dx at the point x is equal to x0, or df dx at x is equal to x0, or d dx of f of x at x is equal to x0. So for example, if u of x is equal to 1 over x, then we could write that u prime at 4, that's the derivative of 1 over x at x equal to 4. That is equal to minus 1 over x squared. Remember, we've done the derivative of 1 over x. Minus 1 over x squared at x is equal to 4. Replace x by 4, we get minus 1 over 4 squared, or minus 1 over 16. Show that the absolute value of x is differentiable between minus infinity and 0, between 0 and infinity, but is not differentiable at x equal to 0. If x is greater than 0, then that's straightforward. If x is greater than 0, then the absolute value of x is just equal to x. Put that into the definition, and we just get equal to 1. So it's differentiable if x is greater than 0. Similarly, it's differentiable if x is less than 0. There's just one difference here. If we take the absolute value of a negative number, then we get minus that number. But what happens at 0? If we're at 0, we try to do the limit as h tends to 0 of absolute value of 0 plus h minus the absolute value of 0 divided by h. We get the limit of the absolute value of h divided by h, but that's the same as the limit of plus or minus 1. This limit does not exist. We can't take a limit of something which is sometimes equal to 1, sometimes equal to minus 1. So therefore, this function is not differentiable at 0. I have maybe 15 minutes left, 15 or 20 minutes left. Would you like to take a break, or should I just keep going until I've finished? Right, it's equal yet. So far 5 and 5. So we need the remaining 11 people to vote. This is very close. 6 people want to break and 5 people don't want to break. And 10 people haven't voted yet. Okay, then let's take a break. We'll take a 13-minute break, and then I'm going to continue at 10 past 7. And let's continue. When, when does a function not have a derivative at a point? If a function has a corner, then the derivative at x0 does not exist. If the graph of a function has a cusp, then again, the derivative at x0 does not exist. If we have a vertical tangent, then the derivative of f at x0 does not exist. If we have a discontinuity, like in this picture, then the derivative does not exist at x0, or we could have this type of discontinuity. Again, the derivative at x0 does not exist. We can take the previous idea and then turn it around. If discontinuous implies no derivative, think back to when we talked about symbolic logic, when we talked about the contrapositive. We can change that around and say, if f has a derivative at x0, then f must be continuous at x0. For the rest of today's lesson, I want to talk about some differentiation rules. We don't want to always be using the definition involving the limit if we want to calculate the derivative of a function. We want some easier ways to do it. And these are the rules that we can use to make our differentiation easier. First of all, if we have a constant function, a horizontal line, what is the slope of a horizontal line? The slope of a horizontal line is always equal to 0. The derivative of a number is always equal to 0. If we have a power function, then the rule is that the derivative of x to the power n is equal to n multiplied by x to the power n minus 1. So, for example, if I wanted to do the derivative of x cubed, we have a number 3 at the front, and then the power needs to decrease by 1. It goes from 3 to 3 minus 1, or 2. The derivative of x cubed is 3x squared. We can also use this rule for square roots or 1 divided by a power function. Why? Because square root of x is the same as x to the power of a half. So using the rule, we have a half at the front, and then the power is decreased by 1. A half x to the power minus a half, that's the same as 1 divided by 2 square root of x. How can we use that for 1 divided by x to the power 4? Well, 1 divided by x to the power is just x to the power minus 4. So we use our rule, minus 4 x to the power minus 5, or minus 4 divided by x to the power 5. We have a constant multiple rule for derivatives as well as for limits. If u is differentiable and if k is a number, the derivative of ku is the same as k multiplied by the derivative of u. This one I'm going to prove. What does the derivative of ku mean? It really means the limit as h tends to 0 of ku at x plus h minus k of ku at x, all divided by h. But remember the constant multiple rule for limits. The constant multiple rule for limits says anytime we have a number, we can take it outside of the limit. And then we just end up with k multiplied by du dx. Just using the constant multiple rule for limits, we can prove the constant multiple rule for derivatives. So for example, the derivative of 3x squared is 3 multiplied by the derivative of x squared. Anytime we have a number, we can just take it outside. The same is true for minus 1. The derivative of minus u is the same as derivative of minus 1 multiplied by u. Take the minus 1 outside. The sum rule. The derivative of u plus v is the derivative of u plus the derivative of v. And again, that comes quite quickly from the sum rule for limits. So for example, if I wanted to differentiate or find the derivative of this function, I can just split this up into easier derivatives. Derivative of x cubed plus the derivative of 4 over 3x squared minus the derivative of 5x plus the derivative of 1. To each one of these separately, we get the answer. 3x squared plus 8 over 3x minus 5 is equal to 0. Does the curve y is equal to x to the power 4 minus 2x squared plus 2 have any points where the derivative is equal to 0? If so, where are they? The first thing to do is to differentiate this function. We get 4x cubed minus 4x, and then I can factorize that to 4x, x minus 1, x plus 1. How can we make this equal to 0? It's 0 if x is 0, it's 0 if x is equal to 1, and it's 0 if x is equal to minus 1. So the answer is there's 3 points where the derivative or the slope is equal to 0. Let's look at the graph of this function. Here they are. Here are the 3 points where the slope is equal to 0. The product rule. If u and v are both differentiable at the point x0, then u multiplied by v is also differentiable at that point, and the formula is the derivative of uv is u multiplied by the derivative of v plus v multiplied by the derivative of u. Or if we use prime notation, the derivative of uv is u prime v plus uv prime. For example, differentiate x squared plus 1 multiplied by x cubed plus 3. I'm going to solve this 2 different ways. First, I want to use the product rule. I have y is equal to u multiplied by v, where u is x squared plus 1 and v is x cubed. X cubed plus 3. So what we do is, first we differentiate the left function and the right function stays the same. And then the left function stays the same and we differentiate the right function. When we do these derivatives, now leave this for you to check, we get this answer. There's another way we could answer this if we wanted to. First, we could multiply out these brackets, and then we could differentiate. And of course, we get the same answer. Our next rule is the quotient rule. Our final rule is the quotient rule. If u and v are differentiable at x0, and one more thing to be careful about, if v at x0 is not equal to 0, because we can't divide by 0, then u over v is also differentiable at this point, and the derivative of u over v is u prime v minus uv prime over v squared. Let me write that back to the product rule. The product rule said that the derivative of uv is u prime v plus uv prime. We have almost the same thing here, but instead of plus, we have a minus at the top. For example, differentiate y is equal to t squared minus 1 over t cubed plus 1. Now we have function divided by function, so we use the quotient. I'm doing u prime v minus uv prime divided by v squared. So I do function on the top, prime, and then function on the bottom stays the same. Minus function on the top stays the same, function on the bottom prime, and then divided by function on the bottom squared. I'll leave this calculation for you to check that this is the answer. Differentiate square root of s minus 1 divided by square root of s plus 1. In the end, we have function divided by function. And let me remind you that we've already seen that the derivative of the square root of s is 1 over 2 square root of s. So let's use the formula. df ds, the derivative of f, is u prime v minus uv prime divided by v squared. That's root s minus 1 prime multiplied by root s plus 1 minus, and then the first function stays as it is, root s minus 1, and we differentiate the second function, the v function, root s plus 1 prime, and then all divided by v squared. I'll leave the details here for you to check. You can check that I haven't made a mistake here, and the answer is 1 over root s plus 1 all squared. Let's talk briefly about second and higher order derivatives. If if f is a differentiable function, then f prime is also a function. Maybe f prime is also differentiable, and if that's true, we can differentiate it a second time, and we get a new function which we call f double prime. F double prime is the second derivative of f, and we can write it like this. We can either write f double prime of x, or d dx of f prime of x, or d dx of dy dx, or d squared y dx squared, or dy prime dx, or y double prime. These all mean the same thing. So for example, if y is equal to x to the power 6, we can differentiate this one time to get 6x to the power 5. We can differentiate it again to get 30x to the power 4. Or we can do this all in one step. First, I have two derivatives of x to the power 6. That means derivative of the derivative of x to the power 6. That's derivative of 6x to the power 5 or 30x to the power 4. F double prime is a function. Maybe it's a differentiable function. If it is, then its derivative, f triple prime, is called the third derivative of f. If f triple prime is differentiable, then its derivative is the fourth derivative of f, and so on. Now, for the first, second, and third derivatives, we use this prime notation, prime, double prime, triple prime. But after that, we change notation. Why? Well, let's suppose I had 13 derivatives. Would I write f prime, 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 prime? No, that would just be silly. Instead, we use this new notation, f bracket 13 bracket, for the 13th derivative. Final example, final slide of today's lesson. Find the first four derivatives of x cubed minus 3x squared plus 2. First derivative, 3x squared minus 6x. Differentiate it again to get y double prime, 6x minus 6. Differentiate that, and we get y triple prime is 6. Differentiate 6 and we get 0. The fourth derivative is 0. Now, before we go on, before I finish, let me just remark that because the derivative of 0 is always equal to 0, we know that all of the rest of the derivatives are also 0. The fifth derivative, the sixth derivative, seventh derivative, eighth derivative, etc. must all also be 0. And that's all I have for this week's lesson. Next week, we'll also cover 4 chapters: derivatives of the trigonometric functions, the chain rule, antiderivatives, and then integration. Are there any questions?